So before we get started, any questions? Okay, no questions, very good. Then let's talk about boundary conditions. We went through boundary conditions in the last lecture, and we are of the opinion that you can look at a partial differential equation, and if you stare hard enough, you know what the boundary conditions are. The reason is because intuitively, if you have a charge, the charge produces electric field and electric flux that looks like this. So if you have a line of charges, the electric flux that comes out of these charges will look something like this. You can see that the charges produce fluxes that are of opposite polarity on the different sides of the charge sheet. So if you were to linear superpose this on top of, say, a field at the background, the total flux produced by the charges and the background flux would be discontinuous. Can you see that? Okay, the discontinuity is proportional to the charge or surface charge density of the surface charge. So we got this n dot d1 minus n dot d2 is equal to rho sub s. Okay, this is one boundary condition that we have derived from Gauss's law. Another boundary condition that we have derived mathematically, but based on the intuitive notion that if you have a piece of wire carrying a current, the magnetic field that you would have would be looking like that from your undergraduate courses. Okay, so if you have a line of current line up to make up a current sheet, okay, the magnetic field will look something like this intuitively. You can see that the magnetic field H1 on one side and H2 on the other side are of opposite polarity. So if you have a current sheet producing magnetic field, and if this is sitting in some background magnetic field H, then the magnetic field is discontinuous, and it's due to the presence of a current sheet. So we end up with this other boundary condition, which actually follows from Ampere's law. Okay, and that follows from Ampere's law. Physically, you can see it from the picture on the left. Mathematically, you can derive it from Ampere's law on the right. Okay, so similarly, if you start with the current continuity equation, the currents must satisfy. So in this current continuity equation, everything is finite on the right-hand side. Because of this, then you can very quickly go through the thinking, show that n dot J1 minus J2 is equal to 0 because divergence of J is finite, just like how we derive this. Over there, we have some surface charges, but we do not have anything that is singular on the right-hand side. So since that the normal component of the current must be continuous, and since we have a conductive medium, the two currents are of this manner, so we end up with sigma 1 E1 minus sigma 2 E2 must be equal to 0. But this seems to be in contradiction with this equation over here. So if you look at this equation more explicitly, you will say that epsilon 1 E1 minus epsilon 2 E2 must be rho sub s. So these two equations seem to be in conflict with each other unless rho sub s equals 0. If rho sub s equals to 0, there's no conflict. Okay, and rho sub s can only be 0 if the epsilon 1 and epsilon 2, sigma 1 and sigma 2 are of a certain type. So most generally, this equation is de Ricco. Okay, it is mandatory because we derive it from here. So when this equation is satisfied together with the other boundary condition, what it means is that in the interface between the conductors, there has to be surface charge density. There has to be surface charge accumulation. Is this understood? So one thing to keep in mind, especially if you're in semiconductor physics, where you have conductive material together with dielectric materials, and the interface of the two conductive media, there has to be surface charge accumulation. So let's look at this picture. This picture is the case of a conductor interfacing with free space, which is air in this case. Okay, air, we can assume that mu is equal to mu naught, epsilon equal to epsilon naught, or that permeability and permittivity of vacuum. So as we said before, there has to be some surface charge accumulation. But before we do that, let's assume that this is a perfect conductor. A perfect electric conductor, you can also call it a superconductor if you want to. So if you do have a perfect conductor, what it says is that the electric field has to be inside or zero inside. You can also show that each field has to be also zero. Everything has to be zero inside a superconductor or perfect conductor. So we can just use some physical argument to explain why. Let's assume that there is a small electric field inside the perfect conductor or superconductor. Okay? Just assume that it is very small, but sigma is infinitely large. So what would be the current if there is a small amount of electric field inside the perfect conductor? Yeah, it goes infinity. So if you have an infinite current inside the medium, it produces an infinitely large magnetic field. Okay, and that is not stable because you know that if you have a magnetic field is coupled to the electric field. So this infinitely large magnetic field, just a little bit of jiggling of it will produce the electric field back again, which in turn produces an infinite conduction current, and that process is not stable. So in order for the process to be stable, this has to be true. So this is PEC of a superconductor. Now if you have this interface between a perfect conductor and air, there has to be surface charges, and very rightly so, because the boundary condition is that n dot d2 minus d1 is equal to rho sub s. Okay, and then we have n dot sigma 1 e1 minus sigma 2 e2 must be equal to 0, but e1 is equal to 0. Okay, which means that the normal component of E2 is not equal to 0. This is not equal to 0. And that is only possible. Okay, D1 is equal to 0. If you plug in here, you get epsilon 2 E2 is equal to rho sub s. Okay. So the normal component of the electric field in the air region must be non-zero in order for these two boundary conditions to balance out and to make sense. So the electric field will look something like that, okay? So this is arguing for the case of a perfect conductor. And you can say that a perfect conductor shields electric field and magnetic field from it. It cannot be anything inside, and if you have a perfect conductor, radio waves cannot get inside a perfect conductor or a superconductor. But you generally do not need that for shielding. Okay. Let's assume that either two conducting spheres or two conducting objects of different conductivities. Okay, let's assume that the frequency is very low, or if it's static. Let's assume that the electric field is not 0 inside both of these conductors. Okay, This does not have to be a perfect conductor, but electric current will flow if the electric field is non-zero inside them. Agree? Okay. So it's not a stable process too if the problem is static. If there is current inside these two conductors, it's not a stable process. So the current will keep flowing until the charges on the surface conductor of these conductors rearrange themselves to produce an opposing field that makes the field zero inside the conductors. Can you see this physics going on? So the charges reorient themselves to produce an internal field that cancels everything inside. So the E has to be zero. E being zero means that there's no current flow, and we reach the quiescent state. The quiescent state being that there cannot be any current flowing inside this conductor. And this conductor, as you have seen in your Duncan experiment, they do not have to be perfect conductors. They just have to be good conductors. You see that? Just as long as they are good conductors, they can move the charges around and shield the electric field from entering it. Okay. So what is more important is that if the electric field is zero inside, we know this to be true. So if the electric field is zero inside, he says that phi must be a constant. Phi being a constant means that these two objects, they don't have to be circular. I draw them to be circular because they're easier to draw. They can be objects of any shape. The object has to be at equal potential, and there cannot be any electric field inside. Okay, if you have an equal potential surface, equal potential object, electric field is zero inside. So in addition to having charges moving to the surface, you can safely say that E1 is equal to 0 and E2 equal to 0. Okay. Anything? Okay. So this is a wonderful thing. The wonderful thing being that you don't need a perfect conductor or good conductor to shield out electromagnetic field. And you probably have heard of the story of the Faraday cage. I have a picture of Faraday cage on the bottom left. And what happens there is that if you can, say, keep the cage grounded so that the surface of the cage is at equal potential. Okay, one way to make it equal potential is to ground it. And then if the potential is a constant on the surface, it's also a constant inside the cage, which means that the electric field has to be zero inside the cage. So if you want to have a radio-free environment to do your experiment, you go inside the Faraday cage. You will receive no radio signals. Because radio signals, even though they are not static, but the frequency is very low, like AM 920. I think the wavelength is on the order of 100 meters. It's going to be a lot larger than the size of the cage. You will learn later on that if the object is much, much smaller than the wavelength, you can consider the problem to be a static problem. Okay. And if the object is not much smaller than the wavelength, there has to be a dynamic problem. So if you have a cage where you do experiments with radio wave at AM 920 or something like that, or I don't know, 101.3 is 100 meters, right? Is that there's 100 megahertz. So the wavelength is shorter there, but still much larger than the size of the cage. Okay. So any questions regarding shielding of the electric field by charges? If not, let's move on to the case of the magnetic field. Magnetic field is a bit trickier because we cannot shield out magnetic field with magnetic charges. There are no magnetic charges in this world, and they are yet to be discovered. Nobody has found them yet. So the only way you can shield out magnetic field is by using what we call Lenz's law. where you push the magnetic field outside, the eddy currents. So what happens is that here's a picture where I have a perfect conductor. There's a magnetic field outside. And the only way you can keep the magnetic field outside is to have eddy currents on the surface of this object. Can you see that? Because the field is zero. Okay, I want the B field to be zero inside. Okay, so you can easily see that N cross B1 is not equal to N cross B2. Okay, because it's zero inside the object, it's non-zero outside. This can only happen if there is a surface current, as we have learned from our boundary conditions. Our boundary condition says that for magnetic field, N cross H1 minus H2 has to be proportional to the surface current between the two regions. Okay? So the only way is to have eddy currents being produced. Any questions regarding the shielding of magnetic field? So shielding of magnetic field is not that simple. You need good conductors. So you can't fill out low frequency magnetic field very easily. You probably have played with magnets when you were young. You can feel that the magnet can go through the conductor and still make iron filing patterns on the other side of the sheet, even if you have a copper sheet. Not a magnetic sheet, but a copper sheet. Okay. So this gives you the interesting physics of magnetic levitation. Okay, magnetic levitation. And you probably have seen this if you have been to some museum of science. I saw this, the last time I saw this was in the Museum of Science in Boston. I don't know if they have this in Chicago. So what we have here is a picture of magnetic levitation. And you have a permanent magnet at the bottom. Maybe it's made of a North Pole and South Pole kind of thing, like this in the bottom. And then you have the superconducting disk. I don't remember what the chemical name is now. Maybe lithium niobate, or not lithium niobate, something, some copper compound that you can make this at almost room temperature, not with liquid nitrogen, but something much easier to cool. So if you have this piece of metal, which is a superconductor, you put it next to a magnet, the magnetic field will induce eddy currents on this superconductor. Okay, the eddy current will produce a magnet of opposite polarity. So what happens here is that naturally, as you take the superconducting coin or shaped object onto the thing, it will develop a magnet of the opposite polarity due to eddy currents flowing on it. Eddy current has to flow on it so that the magnetic field has to be expelled from the superconductor. And the two magnets are opposite polarity, and it will be levitated. Okay, it will be levitated. It's an interesting sight to see. If you happen to be in Boston, you can go to the Boston Museum of Science, you can see it there. Okay. Another place where you can see levitation is those performed by Indian gurus. And they seem to be able to levitate themselves. I don't know how they do that. Okay. So any questions on boundary conditions, shielding of electromagnetic fields by conducting objects and superconducting objects? Okay. If not, let's move on to a different topic. The different topic I'd like to talk about is Poynting's theorem. This will be a time domain Poynting's theorem. Okay, and see what kind of things we can say about energy conservation. So let's assume that we have a time-varying field. Time-varying field, and then what happens is that we know from Maxwell's equations, we have curl of E should be equal to minus dB dt. And then curl of H is dB dt plus J. Okay. You should know these equations like the back of your hands after this course. Okay. You can reproduce them in your dream and in your sleep as well. Okay. So let's make things symmetric, as mathematicians like to do. The Faraday's law does not look like Ampere's law. Ampere's law has an extra term, J, but that's not in Faraday's law. Mathematicians love symmetry. So even though we don't have magnetic current, why don't we put it there just for symmetry and define something called a magnetic current, which is fictitious. But let's imagine that it is there mathematically. And these currents, let's call them impressed current with a subscript R. Okay, this is fictitious and impressed. Impressed means that the currents are put there and nothing can change them. They're immutable. No matter what environment you put this current in, they remain the same. That is the concept of an impressed current. It's like your current source and your voltage source that you learn in your circuit theory. Remember, when you put a current source in a circuit environment, no matter what you do to the environment, the current remains the same in your current source. The same with your voltage source in your circuit theory. You can change the resistors around, but you're not to change the value of the voltage in the voltage source. So these are the same concepts we have here. And let's make things a little bit more interesting by allowing for the fact that we can have conduction current. And that conduction current exists when the medium is conductive. Okay. And let's see what kind of power conservation law we can derive from just these two Maxwell's equations. As we said before, only two of the four Maxwell's equations are important if you're in the electrodynamic regime, because the other two are derivable. So let's play around with this equation and try to derive some conservative laws. So in order to do that, let me dot the first equation with H and dot the second equation with E. Okay, can you see that? So that allows me to do something, because by the time you reach the stage of this level, you are able to play around with vector identity. So you try to look for what divergence of E cross H is. Well, why do we start with such a term? Everything is by motivation and inspiration. E cross H would have a dimension of power density, because what is the dimension of the electric field? Anybody? Yes.
Volts per meter.
Very good, volts per meter. What is the dimension of magnetic field? Very good. So if you multiply these two together, what units do you get? Watts per meter squared. Okay, very good. So this is power density. Okay, power density. And you use the, I guess it's like the back of the cat formula, but not exactly. So this is what we call the rotating formula, a cyclic formula. A cyclic formula that you should know in this course is that A dot B cross C is C dot A cross B is B dot C cross A. We just cycle the dot product around to get this preservation of this identity. But we almost have a chance to use this identity except for one thing. The del operator is a differential operator. So it operates on both E and H. In order to use this cyclic formula, you first have to keep E to be a constant. You apply this cyclic formula, and next, you keep H to be a constant. And then apply this cyclic formula. So not cyclic formula, but cyclic formula. Okay, so you will get that this should be equal to that. Okay, can you see that? We just apply the formula 2 times, taking turn to keep each of the E and H constant, respectively. Okay, it's like the product rule in differentiation. Okay, so now I have curl of E and curl of H. I can go back to Maxwell's equation and substitute in what I have, and then the right-hand side of this equation should be equal to H dot, and taking from Maxwell's equation, this should be H dot minus dB dt minus M sub R. Okay, I have a sign error here. This should be a minus sign. Okay, and if you want to introduce a fictitious current, it is more symmetrical to put a minus sign there. So the 2 of the Maxwell's equations are the same genre. Okay, they have minus sign on the right-hand side. And then the second term, which is this term over here, this should be a minus sign. And now you can substitute in for curl of H, you will get E dot partial D partial T. Plus, let me erase this away. Okay, take this away. Seems to know what this is. Plus JI plus sigma E. Okay. And then they're complicated terms, products of H and its derivative. And those could be simplified. Okay, so if you look at the right-hand side, and if you were to simplify things so that you can think clearly, you can set all these currents to be 0. You can set them to be 0 to begin with. And then things become simpler and we can think with a clear mind. And you will see that the right-hand side is just equal to H dot dB dt with a minus sign, and then minus E dot dB dt. And this could be simplified because B and H are related. Okay, so let's assume that we have the case of a vacuum, permittivity and permeability. So D is just epsilon naught E, and then if you were to substitute this in, you will find that the right-hand side now becomes something like mu naught H dot dH dt minus epsilon naught E dot dE dt. Okay, just after substituting in the constitutive relationship, you have that. But then this can be further simplified because we know that if you were to differentiate the product of 2 terms using the product rule, this will be just equal to, this will be just using the product rule H dot dH dt plus dH dt dot with H. Okay, where again you keep one constant, differentiate, and then you take turn to keep the other one constant and do a differentiation. You have that. But the 2 terms are identical on the right-hand side. So this is just equal to 2H dot dH dt. So you have this identity which says that this term over here, which is just half partial t h squared, where I use this notation h squared being equal to h dot h. Okay, can you see that? You be careful with this notation, because when that notation is applied to complex numbers, it looks very different from when it is applied to real numbers. So at this point, our vector quantity is real or complex? Are they real or complex? Real, very good. We have not gone into the imaginary or the complex world yet. Later on, we will go there, but not at this point. Everything that we are dealing with now are real numbers. So all the E, H, D, B are all real numbers or real vectors. So that identity is not confusing at all in the real world. This just means that, okay? So if you do that, then the right-hand side can be written rather simply. And what you have is that this should be equal to mu naught half partial t h squared minus epsilon naught half partial t e squared. And then you can write this more convincingly as minus partial t of half mu naught h squared plus half epsilon naught e squared. Can you see that? Okay, so you have divergence of this quantity. You have now a very nice law, a nice theorem. The theorem will say that divergence of E cross H is equal to minus partial t of half mu naught H squared plus half epsilon naught E squared. So what does this equation remind you of? You have a divergence on the left-hand side, you have a time derivative on the right-hand side. What does it remind you of? Yeah? Somebody say something? Very good, the current continuity equation. Okay, current continuity equation says a divergence of J, the minus dt rho. And we mentioned previously that the current continuity equation has the concept of charge conservation. Left-hand side J is current flow. Right-hand side rho is charge density. So here we see the same thing. Left-hand side E cross H, we just convince ourselves that that is power density, which is like power flow per unit area. Right-hand side is a change of something. That must be energy density. Okay, so this must be energy density. So you can think of this as energy density and write that this is a pointing vector. We usually call this the pointing vector, okay, which has the meaning of power flow. And this is the energy density. And you can convince yourself that there's energy density by going through the unit check or dimensionality check. And one of the things that we as good engineers do to make sure that we have derived the correct formula is to check if the dimension of all the formulas that you have is correct. Okay, so the quantity that I call energy density on the right-hand side would eventually have the dimension of joules per meter cubed. Okay, and you can do dimensionality check on that. You can go and put in H having the dimension of amperes per meter. Mu naught should have the dimension of what? Do you remember what the dimension of mu naught should be? Very good, Henry per meter. And what about epsilon naught? Farad per meter, very good. So those quantities are related to Henry per meter is like an inductor. And then Farad per meter is like a capacitor. You know that energy density in an inductor is half Li squared or something. Okay, and you can convert Henry per meter to energy. And then in the capacitor, you know that the energy is, I think, half Q squared over B or something, over C or something like that. Okay, so you can show and convince yourself that the right-hand side is in fact energy density. And hence you can write this equation. Okay, this I can call WT. I can write this equation as divergence of the power flow, just like current flow, is the time rate of change of the energy density. Okay. So this is essentially a statement of energy conservation. But in order to simplify the mathematics, I have done some cheating here to make things simpler. I took out the conduction current. I took out the impressed current MI and JI. But you can go through the same process, put them in and redo the exercise again. And it should not be rocket science if you know how to do the exercise for the first one, right? Just add more terms of the equations on the right-hand side. And if you do that, then the conservative law that you should arrive at is the divergence of this, and with all the bells and whistles on the right-hand side being put in, MI and JI, and your equation should look something like this. Okay. And you probably have learned in your undergraduate courses that this is the energy density in the magnetic field. And sometimes it's called Wm. And this is the energy density in the electric field, which sometimes is called We. Okay. And if you add in the bells and whistles of the currents, so what you would have is you have additional term. The additional term being the sigma E dot E plus H dot Mi plus E dot JR. Okay, E dot JR. Okay. And then the thing that you notice here is that this thing is negative, but all these other things are positive. So what it means is that this part, okay, if the energy density is increasing with time, then you have to, if this physically can be explained as such. If this energy density is increasing with time, then partial T will be positive. Positive, so if that is the case, if WT is increasing with time, it needs power flow to supply inside. So S of P has to be negative. Okay, S of P has to be negative in order for it to supply power in the inward direction. But then if you look at this term, the physical meaning of this term is always positive. Okay. Let's see how they close this. Doesn't close. Okay. So this term is always positive, which means that it always takes energy away. If you think of it as being always positive, it is almost like the energy density is negative with respect to time variation. That means it always sucks up energy. So this term always siphons energy from the power flow. Okay, always siphons energy. And these two terms, and let's look at this term first. when does it siphon energy and when does it pump in energy. So if E dot J is positive, then it will siphon energy from the power, just like the first term we had. Okay, this is always positive, definite. It means that if you have a conductor, which is what we learned from electrical engineering as what happens in the resistor. A resistor always dissipates energy. So if the last term E dot J is always positive, that means that you are siphoning energy off from the system. That means that if the electric field and the impressed current are pointing in the same direction, then that system is dissipated. That current source is actually not a current source, it becomes a current sink. Okay. However, if the electric field and the current are in opposite polarity, then it becomes a current source. Can you see that? So the contribution of the last two terms, depending on whether it is positive or negative, determine their roles as a current sink or energy sink or energy source. Okay, so we can take the example of a battery. Say in a battery, the positive terminal of the battery is always like that. And when we connect this to a resistor, the current will always flow from positive terminal to negative terminal in this manner. Okay. However, if the charges are oriented like this, then inside this battery, the electric field has to be like this. You agree? Which means that if this current is flowing around and inside the battery, the current and the electric field are actually of opposite sign. So the battery is an energy generator. It is an energy source because E dot J inside the battery would be, I guess, negative, right? Since E and J are opposite in polarity, so E dot J, J is pointing in this direction. Okay, E is in this direction, so it becomes a current source, a voltage source, or a power source. Okay, any questions regarding this? You can read about this in greater detail in the lecture notes. Here, just briefly describes what happens. Okay. So, I'm going to talk about phasor technique next. It's something that is very close to heart for most electrical engineers. Are there anybody here who has not been exposed to phasors? Sometimes I do get students like that because they come from mechanical engineering. They don't have to study phasors in mechanical engineering. But if you have had undergraduate education in EE, you know what a phasor is, right? Or in the physics department, they might not even teach phasors, they teach Fourier transforms. Okay, but they're the same thing. But I like phasors better because they're simpler. So what are phasors? So I would call this the Poorman's Fourier transform. Because it will have all the advantages of a Fourier transform, but having not to learn everything about Fourier transform to use it. Okay, you can be pretty rudimentary in your mathematical knowledge. You can still use that. So it's based on this Euler's identity that this identity is something that we learn as an undergraduate student, that if you have exponent to a phase function. It has a real part and imaginary part given by Euler, I think in the 1700s probably. Okay, so this is wonderful way to express sinusoidal signals, because then if I have a time harmonic signal, okay, and that time harmonic signals means that they look something like this. Okay, I don't draw very well, but you know what I mean. It means that it just is a sinusoidal signal. Okay, but time harmonic signals have different names depending on what discipline you are in. Can you think of other names for time harmonic signals in this world? So this world is getting increasingly diverse. So we have to learn how to talk to people outside our discipline. Okay, do you know another name for a time harmonic signal? Do you know? What? Alternative current. Yeah, those are used by power engineers. We will call whatever coming out of the power line to be alternating signal. Yes.
A wave.
A wave. Yeah, close, but not exactly. Yes.
Periodic.
Periodic. Close, but not exactly. Yes. A tone. Close, but not exactly. Okay. All of you have some concept of what the time harmonic signal is. But if you were to talk to an optics guy, he doesn't call it a time harmonic signal. He calls it a monochromatic signal. Okay, you know, the word is very colored, right? Monochromatic means that it has only one color. If it has only one color, means that it has only one frequency. Okay. And if you talk to other kinds of engineers, maybe microwave engineers, they would use the term CW. CW stands for constant wave. So if they have a wave that doesn't change in its period, okay, we call it a CW signal or time harmonic signal or monochromatic signal. And if we have a time harmonic signal, you can easily argue that at every position in space, okay, it can be written in this manner. At every position in space, it can be expressed as such. And different positions might have different phases, okay? This is the amplitude. And this alpha can also be a function of position, okay? So you can convince yourself that this is the case. So what happens then is that I can write this more succinctly as V prime x, y, z, the real part of e to the j omega t plus alpha. Okay, I can write it as such. This is just the use of Euler's formula, because if I take the real part of this, I get this part. So I replace the cosine with just the real part of the exponential function. And then I can write this more compactly by taking the real part outside, okay, and rewriting this part as e to the j alpha times e to the j omega t. And then regroup this and write it as v prime x, y, z, e to the j alpha times e to the plus j omega t. Okay, electrical engineers like to use the fact that -1 and the square root of it is j. Do you know the historical reason why electrical engineers? Or is it because electrical engineers are quirky? Yes?
Because you use I all the time.
That's right, very good. Electrical engineers started out using complex notations quite early. And in olden times, the current I and the alphabet I is reserved for current. So we started to use J to denote a current, but unfortunately, when it comes to Maxwell's equation, we use J to denote current density again. So there is confusion there again, okay? But electrical engineers always use J to denote the square root of a complex number. If you talk to a physicist, mathematician, or even an optical engineer, and we have many of them in our department, ECE, they will use I to denote square root of -1. Okay. And so instead of using e to the j omega t, they also like to use e to the minus I omega t as a time convention. So let's move on and go on with this. So what I can write this as is that this is actually the real part of a complex number, which I call E tilde, x, y, z. Okay, and call this a complex number. It's not writing really well, but maybe we'll change pen. So I can write this as a complex number. I would denote the complex number with an under tilde. I hope it writes better now. Okay. So what I have is that I have a real signal. It can always be written as a complex number times e to the j omega t, taking its real part. Okay. And this part is often called the phasor representation. Complex number. Okay. And then you can see that this is usually called a phasor. I don't know why my thing doesn't write well now. This is called the phasor representation of this signal. Okay, this complex number, not actually the other part, just the first part. Okay. Just this part, which is the complex number, is called the phasor representation of the sinusoidal signal, or the CW signal, or the time harmonic signal. Okay. So this is wonderful because this expression is very nice to differentiate. Whereas a cosine is not that easy to differentiate because when you differentiate a cosine, you get a sine. When you differentiate a sine, you get a cosine. So if you express things in terms of exponential functions, they're very nice to differentiate, as you will see in a little while. So if we have a sinusoidal signal like E of RT, if this is sinusoidal, and this is a field, and it can have its x component and its y component plus its z component. PowerPoint not responding. Okay, and if they are really sinusoidal signals, I can always use the phasor technique and write them as a real part of a complex vector, like Ex, a complex number, which is only a function of position e to the j omega t. And I can do likewise to the second term, and do the likewise to the third term. Okay, if each of the component is a sinusoidal signal or time harmonic signal. In short, I can write this if I aggregate all of them together as a complex vector now, which is a function of position times e to the j omega t. So a real signal can be written as a real part of a complex signal, which is called a phasor representation times e to the j omega t. The only new part here is that E is a vector. And if you have taken other undergraduate courses, E usually is a scalar. Okay, but you can go through the thought processes, whatever you learn from scalar can be applied to a vector also. So what is so great about this? Well, it seems to make life more complicated for you, but not actually. It makes life simpler for you. Because if you were to go into Maxwell's equations and rewrite Maxwell's equations in this manner, okay, like for instance, if I have BRT, if this is time harmonic, I can write this as the real part of a complex vector e to the j omega t, right? Now, if I were to differentiate this equation, this is something that you might already learn in circuit theory as well. When you do the time derivative, the right-hand side just becomes very simple. This is the only place where time dependence comes in. So it can be written as the real part of j omega be a complex number e to the j omega t. So the simple rule of thumb is that whenever you see a time derivative, just replace it with j omega. Okay, and that happens in the Fourier transform technique too, but we don't have to learn Fourier transform to get here. Okay. So the rule of thumb is that whenever we have partial t in the phasor world or in the Fourier transform world, it just becomes j omega. And then Maxwell's equations is greatly simplified in a sense that, for instance, if I write down Ampere's law or Faraday's law, say if I have Faraday's law, which is essentially just this to be simple, then if I represent it with phasors, I can write this as the real part of curl of E tilde e to the j omega t. And then the right-hand side is the time derivative. Okay, you can write this real part of j omega b r e to the j omega t. Okay, so you have this more complicated equation, which seems to be the baggage or the disadvantage that has been brought upon you. But you realize that you can actually remove the real part. There are packages that you don't have to carry around yourself, and you can say this equation is the same as this equation. And I can even take out the e to the I omega t because it will be there everywhere anyhow. Okay, there should be an R dependence here to be precise. Okay, so Ampere's law, there should be under tilde here. Faraday's law just becomes this. Because you can convince yourself that the real part, the real operator can be removed. Okay, the real operator can be removed, and then Faraday's law becomes very simple. The same thing with Ampere's law. In the phasor world, it will become, if these are all the phasor representation, then I should have a minus sign somewhere. I should have a minus sign here. I should have a plus j omega. I can do the same to my j as well. Okay. This is Ampere's law in the phasor world. And then you have the other two laws. Okay, they remain essentially of the same form. You can go to the thought processes and convince yourself that all the four Maxwell's equations become something like this. The great thing about these four Maxwell's equations is that there's no more time derivatives. They're only space derivatives, making them simpler to solve. Okay. So now we can work with complex fields, and they're the same as we working with real fields. Okay, we can replace all real quantities that we have with complex fields. The advantage is that whenever we see a time derivative, we just replace it with j omega. Another advantage is that you can arrive at a Poynting's theorem for complex fields, and that is called a complex Poynting's theorem. What we have derived a minute ago is called the real or the instantaneous Poynting's theorem. Okay, so we have earlier shown that you can have an instantaneous Poynting's vector, and that instantaneous Poynting vector is just the cross product of the instantaneous E field and H field. But now in the phasor world, if these are truly time harmonic signal, you can have a complex Poynting vector. It's no more a function of frequency because frequency is assumed to be the constant. And then it will be the cross product of two complex vectors. Okay, it will be a cross product of two complex vectors. And these actually are functions of frequencies, but we don't explicitly write them down. And then you can actually go through the argument from Maxwell's equations. You can actually show quite easily that Faraday's law is just this. And let me not write, maybe I just still write them down. Okay, Faraday's law is just that. Ampere's law is just that. Okay. And again, you can go through the same exercise as we did before, but instead looking for something like E cross H complex conjugate. Okay. The reason why we put a complex conjugate there is that we have been motivated by circuit theory. In circuit theory, what is the definition for complex power. In ordinary circuit theory, we have this being instantaneous power, but if V and I are converted to be phasors, you see the complex power is this, okay? So this is real power, but this is complex power. So by the same token, we defined a complex pointing vector. Sorry, there should be a complex conjugation over here. Okay, to have everything come out correct. And we have been motivated by circuit theory, so we put in the complex conjugation there. And you find that you can now take the divergence of this quantity, and then you go through the vector algebra again. Okay, which is actually done in the lecture notes. You'll come up with the conservation theorem for complex powers, which I have derived in the lecture notes. But we can derive it quickly, but you see what I have is that, let me see. Lecture notes is here. Can you hear me if I don't wear the microphone? So I actually don't have to wear it, right? Otherwise, I mean, like trapped. Can you hear me? Okay. So then that will allow me to move around the room more easily. So if you go through the algebra for this, okay, very similar algebra that we had before. Okay, we have the complex pointing theorem, but actually I'm not getting there in this lecture. But I'm getting there by proving that if you have two quantities, Vt, It, okay? If this is sinusoidal and this is sinusoidal, and if you were to take the time average of this product, okay, it is equal to the half the real part of the phasor representation of this times the phasor representation of this. This is a very important identity. You need me to prove this, or it has been proved to you in your undergraduate course? It's been proved to you, right? So you know this identity. And using this identity, you quite easily show that if I have this instantaneous pointing vector, if I were to take its time average, okay, and it will become the half the real part of E cross H. Okay. Again, the devil is in the detail. You go through all the phasor things, and if you work things out, taking time averages, you find that this relationship is very similar to what you found in circuit theory. Unless you want me to prove it, I'm not going to prove it. Okay, it's proved in the lecture notes. You can read and go through the lecture notes carefully. You will find that this is the case. Okay. So this is usually called the time average pointing vector. And it's half the real part of that. And you will find that a complex pointing vector corresponds to something which is complex, okay? So very much similar to the case of circuit theory, if you have a complex power, this number is a complex number. That complex power has its real part and an imaginary part. And the real part is proportional to the time average of the instantaneous power. Does anybody know what the imaginary part of that power the physical meaning of that is? Anybody knows? In circuit theory? Yes?
Isn't it the reactive power?
Very good. Okay, it's called the reactive power. Okay. The reactive power will not be there if B and I are in phase. But if B and I are out of phase, then you will see the role of the reactive power. Okay, so I can illustrate you a very simple case of a simple circuit. So if I have a resistor and an inductor, and in this circuit, the current I and the voltage V are out of phase. And let's assume that these are all phasors. Okay, and all of us know how to solve this circuit problem. And from circuit theory and the phasor world that we learned in circuit theory, the impedance is a complex number. The VI relationship between them is this very simple thing, which means that V and I are not in phase. So when V and I are not in phase, if you look at the complex power, okay, and if I go through the detail of this thing, and I can write, say, my IT, instantaneous current, as being not in phase with the voltage. I can write this as real of a complex current times e to the j omega t. And without loss of generality, I can write my V as V naught cosine of omega t. Okay, and with these two current and voltages, if I multiply together, I will get my instantaneous power. Okay, you can actually work out the instantaneous power. It's just a product of these two terms. I'm running out of power to V naught, I naught, cosine of omega t plus alpha cosine of omega t. And then there's some trigonometric identities that you can use to simplify this. And what you will find is this thing, actually I expressed here. Okay, you work things out and you do the trigonometric identity. You'll find that if the voltage and the currents are out of phase, you will have a very strange phenomenon. The top picture is when alpha equal to 0, the voltage and current are in phase. No instance do you see that the power is going negative. However, if the current and the voltage are out of phase, there are instances where the total power is negative. What this means is that their power traveling from the load to the source. Okay, so power delivery is not one direction. The top picture, the current and voltages are in phase, so the power is always going from the source to the load. But in the bottom, you have cases where the power is going from the load to the source. That happens in our home if we use a lot of machinery, like inductors, transformers, and the kind of thing, plastic. Okay, and then the current and the voltages are out of phase, which means that you're actually sending power back to the power generation company instead of always receiving power from them. Okay, in order to run heavy machineries in your home, you need reactive power. Okay, you can see that. Without reactive power, you cannot run heavy machineries. Maybe you can not even run your computers because there are transformers inside. You will not have refrigerator in the home. The power company charges you for both the real and the imaginary power. Because imaginary power, they still have to send to you through the power line. The power line is dissipated. Some of this reactive power will be lost in the power line. Okay, it's written up in the lecture notes. I'll let you read that part more carefully, but it's a concept that's not taught in very many circuit courses. Okay, if you have gone through many circuit courses, and this concept has not been belaboured. Okay, see you next week. And if you have any questions, let us know. And thank you all for coming.